Okay, guys, we can start now. So today we will have the third practical for this semester. We have the column buckling testing. Last week we had the beam deflection. Have you finished the report for the beam deflection, or have you seen the video? The video? Anyone have finished the practical for last week? Can you access? Can you access the video? No one tried. Okay. Okay. Thanks, Mike. So today we will have the last practical for this semester, the column buckling. I will just briefly introduce the practical and then start explanation for you. Okay, so this practical will be the testing columns. The column is a vertical member, as you can see here. So we apply like vertical load or axial load on the column. And when we apply axial load, the column start to deflect horizontally at the mid height. So this deflection is called buckling. So for beams it's called deflection, but for columns it's called buckling. Okay, because the loading is axially load, but in beams the load is transversely. Okay, so this is the column buckling phenomena. And what will we do is testing the columns. This is a photo for the setup. The blue is a testing rig or the frame for testing, and this thin member is a column, and we will have like piston at the top and piston at the bottom, just working as supports at the end or restrictions at the end. And we will apply this small loads here to the right of the photo gradually until failure of the column due to buckling. Okay, this weights like we introduced them last week. So each weight is 5 Newton. So we will apply 5 by 5 until failure of the column. Okay, this is the piston, and this is how to apply the weight or the load. So each one of them is 5 Newton. Okay, so this is generally what we do, and now I will start explanation to you using pen. So what will we do today is comparing the experimental result like last week with the theoretical result. So we will have a comparison between experimental and theoretical. So today class or practical is column buckling. And the meaning of column buckling is that if we have a vertical member column, and the column should be supported from the top and supported from the bottom. If we apply a vertical load or axial load B, so the column will buckle due to applying the load. Okay, so this is buckled column or buckling. And the maximum deflection will be at the middle of the column delta. Okay, so this is called buckling phenomenon. The load causing buckling or causing failure due to buckling, we call it BCR. or B critical. So B critical or B Euler is equal to pi square EI divided by L effective square. So this is the formula for buckling load. B critical or BCR or B Euler is the critical buckling load. This means that the load that will cause failure due to buckling. I mean the maximum load before failure due to buckling. Okay. The parameter for this formula are E. You know E from last week is material properties or Young's modulus. Exactly. It presents the material. So E is the Young's modulus. I is the inertia, depends on the cross section. So if the cross section is square, different from rectangular, different from circular, and so on. So the inertia depends on the cross section shape. L effective or LE is called effective buckling length. This means the effective buckling length of the column. Okay. What do we mean by effective buckling length? This length is the actual length of the column. L. L effective has also a formula. L effective equal to a factor K multiplied by the height of the column or the length of the column L. So L effective equal to K multiplied by L. Where is L? Column length. So, and K is the buckling factor or effective length factor. Buckling factor. Okay, and L effective is effective length as we mentioned. So this is effective length. Okay, so to know L effective, we need to know K. Okay, we need to know K. So what is K? K is the buckling factor. Depends on the type of two ends. So K depends on column ends. If we have a look here, so we have top end of the column and bottom end. The top end and bottom end is controlling our K. Okay, so I will now shift to the next slide to explain what is K. So L effective equal to K multiplied by L, where K has three values. K will may equal to 1, or K equal to 0.5, or K equal to 0.7. So the K value has three values, depend on, again, column ends. Okay, we have three cases. If the column is bent from the top, this is the indication of bent support, and also bend from the bottom. This column called bend or bend. So this first case. If we have a look here, the length of the column, this is L. If this column is under axial load, this column will buckle in this shape. Okay, and L effective is the distance between the zero moment at the top to the zero moment at the bottom. So this will be L effective. So what is the relation between L effective and L? For this case, L effective equal to L. This means that K is equal to 1 for this case. So you need to keep in mind that if the column is bend, this means that K is equal to 1. The second case we have, if the column is fixed column. So second case, the column is fixed at top and also fixed at bottom. So if this L, this column will buckle in a different shape from the first case. It will not buckle for some distance at the top and also from some distance at the bottom, then start to buckle like this. So it has different shape. So the zero moment here will not be from the beginning or the start of the beam. It will be somewhere here. There is a moment for this column, and this is the zero moment here, and this is zero moment here. So the distance between the two zero moment is L effective, and is nearly half of the total height of the column, so it is 0.5 L. Okay, so for this case, K is equal to 0.5. So if the column is fixed, K will equal to 0.5. The third case is a mix between the two cases. So if we have column, one end is fixed and the other end is hinge or bend. So this column is case 3, fixed bend. Or it may be the reverse. If the top end also is bend and the bottom end is fixed. This is still fixed bend column. So what is the deflection shape or the deflected shape? Here the deflected shape will be at the top, the column will not buckle for some distance, but here it will buckle from the start. So the deflected shape will be something like this. And here as well, the deflected shape will be something like this. Okay, so here the distance between 0 moment and 0 moment here is this distance. So if this L, the total length is L, this is something between 0.5 and 1L. So they assume or mention that LE will be nearly zero point 0.7 from the total height L. Here as well, from here to here is L effective equal to 0. 0.7 L. So this gives us that if the column is fixed bin or bin fixed, K will equal to 0.7. So this is the three cases we need to know. K equal to 1, K equal to 0.5, K equal to 7. Okay, so using L effective and returning back to the Euler equation, B critical equal to pi square E I divided by L effective square. So if we need to know the buckling load or the failure buckling load for a column, what we need to know is the type of the material E and the cross-section shape to get I, and then know effective length buckling using K equal to 1 or K equal to 0.5 or K equal to 0.7, depending on the two ends of the column. Okay? Do you have any problem in this formula? This formula is the theoretical formula for buckling of column. So this is if we need to compare with the theoretical equation, we will use this equation. Okay, so this is generally the buckling equation or the buckling formula for column, which we will compare using this equation with the experimental work. Okay, so the next slide will be the practical itself and how we will do the practical if we are doing it in the lab. Okay, I will return back to the project description to show you. Here, if we have a look here, so this is our buckling formula, or this one. B critical equal to pi square EI divided by L effective squared. And here, this is are the three cases we have. Okay, if the column is bend ended or bend, this give K equal to 1, fixed K equal to 0.5, bend and fixed ends equal to 0.7. Okay, now the next step is to do the testing. This is again the testing rig we have, and we will have 9 samples to do or 9 tests to do. Okay, so we have 9 tests from 1 to 9. They are similar procedure, but just repeating with different type of roads or different type of material. So now I will explain to you the details of the testing. So now here, the practical. We will have in this practical 9 columns or 9 tests. These 9 columns are divided to 3 groups. Group number 1 is 3 columns. The common thing between these three columns is the material. These three columns are from stainless steel. Okay, so these three columns is from stainless steel. And all the columns are circular columns. So this column are circular columns from stainless steel. Stainless steel given to you in the project description, E for stainless steel equal to 193,000 MBA. Okay, so we have three steels with three samples from stainless steel with E equal to 193,000 MBA. And under this group, we have three type of column endings A, B, C. Just to compare between them, the first column will be bin or fixed whatever. Second column will be fixed, and the third column will be fixed bin. Okay, so this is the three columns we have for each group. So first group from stainless steel, bin, fixed bin. The second group or group 2, also three columns, but from different materials. The material for second group is E, or sorry, the material first is mild steel or normal steel. So mild steel. And given E for mild steel equal to 200,000 MBA. Okay. And under this group, we will have again similar three columns A, B, C. Bin, fixed, and fixed bin. Okay. So just similar repeating but with different material. The last group or the third group will be group number 3. Also from 3 columns. And the columns again are circular columns with diameter D. The material for this column is aluminum, not from steel this time. Aluminum. And given E for aluminum equal to 73,000 MBA. And under this group again, we will have 3 different column ends A, B, C, bin, fixed, and bin fixed or fixed bin. Okay, this is a description for the columns, for the 9 columns we have, and I will show you in a table in the description. As you can see here, this is a test sample description. The first 3 samples are from stainless steel with E equal to 193, and the 3 cases of fixation or support at the end are fixed, bend, and bend. And this is the actual sample length. Just to you will know later that this length is different lengths to simulate the fixation or the end supports. Okay. The second group from 4 to 6 are from mild steel with E equal to 200,000 and 3 type of supports and different lengths. The last group will be from 7 to 9 from aluminium, 73,000 MPa young modulus or modulus of elasticity, and different lengths. Okay. Now the second step is explanation for the test rig and how to do the test. Okay. So now, do you have any question till now?
Was the mold still cross section circular?
Yeah. All the samples are circular.
Yeah.
I will just okay. I will add it here. So also here the group the samples for group 2 are also circular with diameter D. Okay, if we are doing this in the lab, your rule will be to also measure the diameter for each sample because they have some small variation to get the dimension for everything. But now we are just doing it online, so you will get the results from the video or the values from the video. Okay, so now the second or the next step is to explain the test rig and how we do the test. So the test rig is the frame. This is the base or the foundation of the frame. Okay. And at the top of the test rig, we will have piston. And at the bottom, we will have another piston. This two piston is just to simulate the supports or the ends. And at the middle or at the mid height of the frame, we will have a ring, circular ring, and we will put the column in the two piston here. Okay, and then start testing. How to start testing? What we will do is just adding the loads one by one, and as we mentioned that the load is small weights. Each one of them is 5 Newton, and we have again 10 like last week. So the maximum load we have is 50 Newton. So you will expect that all the 9 columns will fail on before 50 Newton or at 50 Newton. Okay. So what will we do if we apply the first one, the green load? The column will buckle a little bit, something like this, but still not failed. And what we will do is using a vernier capillary, we will measure the distance between the ring to the, so if this B1, so this delta 1. So we will do this in table. The load and the deflection or the horizontal deflection. At 0, there is no deflection. At 5 Newton, maybe let's say that this will be 30 millimeter or whatever. At 10 Newton, let's say 25, because if the column buckles, so it will reach or become near to the ring. So second step is applying the second load as we mentioned in the table. So the load will buckle again or buckle more, and then we measure the distance again. So this is delta 2 and so on until failure. What indicate failure? Failure here, we will consider failure if the column touches the ring. So if the column touching the ring, this means that the column failed. So if we apply, let's say that after applying until 40 Newton, so the column just touches the ring here. This is at 40 Newton. So at 40 Newton, the distance between the column and the ring will be 0. So this considered failure load or B critical. So B critical is when the load or when the column touches the load, touches the ring. So this is B critical. Okay, I will just return back to the column, to the project description here.
Ahmed, I've got a question.
Yeah, sure.
So can you please open the previous slide, that the ring one?
Okay, I will repeat this again. Sorry. Just okay here. If you have a look on this table,
All good.
yeah, I will repeat for you. For this table, can you see the table now?
Yep.
This is the
Yeah.
table. We for each test, what we will do is just adding load at 0. The deflection will be 0, and the deflection is the maximum distance from the outside ring to the rod. So we are measuring from the ring to the rod. Okay. At 5, the distance will be, let's say, 30. At 10, maybe 25, and so on. So because when we apply more loads, the column is touch or get closer to the ring. Okay. So let's say that the column touches the ring at 40. So at 40, the distance will be 0. Okay. So let's say this 22, 18 or 17, 12, 6, 3, and so on. Okay. So we don't have to add more loads because more loads doesn't make sense, because this is the maximum distance that the column can move. So no more adding load. So there's 45 and 50 is not applicable here. Okay, and the maximum load be critical for this case is 40 Newton. Okay, do you get this one? And we will repeat this for each test. Okay, so I will return back to the test. I will repeat explaining the test for you. So again here, we have, this is the frame. For the testing frame, we have piston at the top and piston at the bottom, and we have a ring at the middle. Okay, what we will do is putting the rod between these two pistons and applying the load. But just before going to this step, I just forget something to explain to you: how to simulate the pin and fixed support. If we have a look on the piston, this is the piston. The piston has two holes, one at the top and one at the bottom. Okay, so this is the piston. The upper hole has a depth of 11 millimeter, and the lower hole, or the lower at the bottom, is the hole at the bottom is 1 millimeter depth. So we have 11 millimeter and 1 millimeter. 1 millimeter, we will use it to simulate the bin support. The 11 millimeter, we'll use it to simulate the fixed support. So if I want to make the column bin, what I should do? So this is the piston. This is the small hole. So we will put the column in the small hole here. And at the other side, the other piston will be as well in the small hole. So this end is bent because we use the 1 millimeter hole, and this hole also is bent because we use the small hole. Okay, and the other hole is the other side is not used in this case. Do you get this one? If we want to make it fix it, we will reverse the direction of the piston and use the bigger hole, and this will be the column here. And also the other side, we will use the bigger hole of the piston. So this support is fixed, or this end is fixed, and this end is fixed. Okay. The third case, if we want to make it bin fixed, so one of the ends will be using the bigger hole here, and this will be the column in the bigger hole, and the other end will be the smaller hole here. So at the top, because we use the bigger hole, so this will be fixed. And at the bottom, because we use the smaller hole, this give us bin. So this is the three cases we have. This is case number 1, fixed. Case number 2, bin. And this is case number 3, fixed bin. Okay. Did you get it, Sig?
Yep, but I just got a question regarding the thing. Like as you said, when the load is 0, so the deflection is 0 as well.
Yeah.
But the
Oh,
deflection,
sorry.
yeah, the deflection should be equal to the radius of that ring.
Yeah, you are right. Sorry for this.
Yep.
The deflection, yeah, I mean, yeah. If you measure the radius or the distance before adding any load, so the distance from here to here is at 0 load. So this, call it R or whatever R. Let's say R is 335 or something. Okay.
Yep. One more thing, as like here we are considering the the depth of that hole is 11 and 1, so the length going to be decreased.
Yeah, that's why if we return back to the project description here, if you have a look here, the distance, the length for the fixed is 600, because you will lose 1100 at the top and 1100 at the bottom. And here is 590 because you will lose 10 or 11 millimeter at the top or at one end. Here is 580 because you will not lose any of the length at the top or at the bottom.
Oh, so they've already compensated this effect in the lens.
Yeah. It's
So we
already,
don't.
yeah.
So we don't need to do anything with the length. So we just use it and put it into the formula of effective length.
Yeah.
All
But
right.
because here, this is the experimental, you are not using the formula, right? Because now, just I will explain one more thing here. Here, the length here, from here to here, from here to here, the length is
We
given,
can't. We
yeah,
can't.
given
Can't.
600, right? You can see this one? Yeah, here for the first case, can you see now?
Yep.
So from here to here is 600, but because you lose 10 millimeter at the top and 10 millimeter at the bottom, so this give you 580, right?
Yep.
Here as well, given to you directly 580. Okay. Here the length is 590, but because you embed 10 millimeter in the top or in the top of the column, so the clear distance or the clear length will be 580. So the length for all of them in the testing, just to compare, is 580 millimeter. Okay. So the length should be similar to compare. But here he gives you in the lab different lenses because you will lose some of the lenses to simulate the fixation or to simulate the support. Okay, do you get it now?
Yep. Just
Okay,
get
but
get it.
this not ill effective because ill effective only in the formula. Okay.
Yep.
Okay, so this is the different lenses or the different procedure for the fix it and bin and fix it bin. Okay.
So for the second pin and pin, they have given 580 already.
Yeah.
But should we need to exclude those 1 meters from top and bottom, or it's fine? We just take 580 as it is.
Yeah, but 1 millimeter is nothing because it should be like collapsed or supported at the two ends.
Oh, okay. So we should just consider 580 in all of these three cases.
Yeah.
All good.
All of them are 580.
Yep. All good.
Okay, so I return back to the test. If we return back to the test here, for each case of them, what we will do is just simulate the end. The top end is bin, let's say bin, and the bottom is bin. So we will first adding the first load. So this is the first load. Then we measure the buckling or the column will buckle a little bit. So we will measure the buckling. Then adding the second weight or the second load, and the column will buckle more. Then you record the buckling, and so on, adding more load and more buckling until the end, the final load, the column will touch the ring. So when the column touches the ring, this means buckling. Okay. But what will happen if we have like two near values for the buckling? I mean, if the column was nearly touching at 35 Newton and 45 Newton. This means that the critical load will be somewhere, the load or the critical load will be somewhere between both of them. Because you cannot exactly get the buckling load using this type of testing, okay? Because you have only 5 Newton. If the load is between the two 5 Newton, so as just roughly we will assume that the load is something between 35 and 40. So the medium between them is 37.5. Okay. So what I mean is if we put 35 and it was nearly touching or very close to touch, so we need just small load. But if we adding the more 5, it will touch aggressively the ring. This means that the load will be somewhere between 35 and 40, and we will take it the medium between them, so 37.5. Okay. Do you have any
Uh,
problem with the test?
Yep. So if that column was just very close to the touching, and then we just put 5 Newton on it, can we just also take, if it was very close to touch, can we also take 36 at that point, maybe for example?
Yeah, yeah, it will be like using your engineering sense. You
Yep.
can, yeah. But if you don't want to apply your sense, so it will be the yeah, something
got
between, yeah,
got it.
because yeah, yeah, because it depends on what you feel or what your sense guide you.
Yep, got it.
Okay, so do you have any problem with the test?
Nope.
So what this is what we will do, just repeating this for the nine samples. Okay, so I will return back to the description again. Here is the piston. As you can see, the piston at the top is 11 millimeter, at the bottom is 1 millimeter. This bottom hole is just to represent the pin end. The top is just to represent the fixed end. Okay. And here is how to measure the distance or the deflection using the vernier capillary from the outer ring to the column. And here is again how to apply the load. And here is the failure or the column at failure. Here, as you can see, the column is touching the ring, so this is considered failure. And here is the table we need to fill to submit the report. This is the first table you need to fill. For each beam, for each column, sorry, you will just adding loads from 0 to whatever the load of failure, 5 by 5, so 5, 0, 5, 10. Not all of them will fail at the same load because they are different materials. Like if you have a look on the last three may fail at 5 Newton or from 5 to 10. Why? Because the aluminum is very weak material, so it will buckle easy. But the first three is the strongest material because it is stainless steel. So you will assume that this three will not fail at low loads. And here from 5, 4 to 6, from 4 to 6, it is a material between the weak and the strong. So it will be a little bit less than the stainless steel and much more than the aluminum. Okay, so this 9 is just a repeated procedure, and the next step is just to compare between the experimental work and the theoretical work. Okay, so to do this, we will fill this table. For test one, as you can see, test one, the first column is fixed. So K factor is 1 or 0.5. So K is 0.5 for the first case. The length of the rod is 580. And the effective length, if the column is fixed, and K equal to 0.5, so effective length will be 0.5 multiplied by 580. Okay. The diameter of the rod, you should find the diameter of the rod, or you will get the value from the video. Let's say 4 millimeter. Then to apply in the formula, we need I. So do you know what is I for the circular section? Do you know what I? How can we get I? So I will explain to you here. If we have a circular here, so the diameter for this circle is D. And the diameter is D. So I will be Ixx will be by d to the power 4 divided by 64. Okay, so this is I for circular section or for circle. Ixx equal to by d square divided by 64. So if we return back to the table, we can get I, and the modulus of velocity for test 1 is 193,000. So using the formula, B critical will be something, let's say 38 Newton. And from the testing, let's say we get it 40 Newton. So this is a comparison for the first case. From the test, we get it 40, and from the formula 38. Okay, and so on. So we will repeat this for each of them to fill this table. The last table is just a summary for what we have done. So we will put here the load from the test. We will put here the load from the formula, and here is the accuracy or the difference for the formula. So using these two values, you can get the difference percentage. Okay. Okay. Do you have any questions?
No, it seems pretty straightforward.
Which one is more like accurate one, theory or observed one?
Here the experimental will not be accurate because you need to add 5 by 5. To make it accurate, you need to add, like, the step need to be less, like adding 0.5 or 1 at least.
Yep.
So, but actually for testing is more accurate than the theoretical, because theoretical is just like assumption or has some assumption. But here for this testing, you may say that the observation or the testing is not accurate just because we don't have the facilities to make it more accurate. Do you know what I
Yep.
mean?
Yep.
Okay.
So the percent difference here will be 40 minus 38 by 40 times 100.
Yeah.
Yep.
Just to see what is the difference, like for 20% or 10%, and there is some accepted tolerance between the testing and the theoretical. You know, if the difference is within 20%, so it is acceptable. If more than this means that you have a problem in the testing or in the formula substitution.
Oh, got it. Yep.
Okay. Do you have any questions now? Can you access the videos, or you need to send you the links?
Yeah, if you could, I haven't been to the links. If you could send it.
Okay, I will send it to you by chat now. Do you have any more questions regarding the practical?
No, just a request. If you could go to the first slide because I was a bit late. I haven't seen what you just wrote in the first slide.
Okay, I will show you. I just sent the links and then go back. You can find the videos links under the assessment, under
Yep.
the learn online site.
Yep, just having a look on it.
You will find assessment. You will find project 2 and project 3. So,
Yep, got it.
okay, I will send you as well here. The first link is for the beam deflection, and the second link is for the column buckling. So this for last week, the first one for last week, the second one for this week.
Yep, thank you.
No worries. Okay, so if we return back to you need the first slide, the first draft.
Yes, please.
Okay, this one. So this is the first one, the first slide we we did
Yep,
last today.
yep.
Can you see it?
Yep. So the delta here, is it same as we are doing in the experiment? The delta that you're showing with the orange color on this first diagram.
Yeah. Here, this is the formula or the theoretical formula.
Yep.
Theoretical
So
form. Oh, yeah.
my question is, the delta here is from the reference of the point where the rod was straight and then the rod is
Yeah.
bent, the distance between those two. But the delta in the
Yeah.
experiment is from outside of the ring to the point where the rod is bent.
Yeah, that's why when I put zero deflection at zero loading, but because you cannot like the reference, this reference is not uh, you cannot see in the test. So
Yeah, because the rod is
yeah,
already bent, so we can't figure
yeah,
it out.
because it will move from this. But you can do this if you know the radius. So your reading, you subtract it from the radius, give you the deflection. But because
Got it.
we will not use this deflection in any calculation, so it doesn't matter.
Yep.
Just like percentage or
Um, One more question, Ahmed. Have you recorded the previous session of last week's tutorial?
yeah, and I also recorded this one.
Uh,
I sent you an email with the link. Did you get it? Or
I might have not checked it, but if you sent it, it will be there.
okay, I will send this one and last week together to you.
Yep, thank you.
No worries. Do you have any other question, guys? You have more question?
No, all good from my side.